Okay. Okay, good morning, everybody. That will be a good morning here in Nigeria, and I will say good day to everybody all around the world that are joining us this morning. We really appreciate your presence here. Thank you so much. So without taking much of our time, I'll go straight to starting the program while we admit others into the webinar as we progress. Thank you so much. So today we'll be looking at machine learning with tidy models. So today, so the agenda for today is going to be, we're welcoming our participants now. So then we're going to go through the agenda. That's the first thing is welcoming you all. We really appreciate your presence here, and we're looking forward to meeting your expectations as you join this webinar. Thank you so much. So the next thing here is to introduce the organizers. I'm Bilikitu Adenrito. I'm a business data analyst, and I'm based here in Abuja. Okay. So, okay. Okay, to start the introduction again, I'm Bilikitu Adenrito. I'm a business data analyst. I'm based here in Abuja, and I'm the coordinator of Abuja R User Group and the R Ladies Abuja. So we have other coordinators, but unfortunately we're not having them on seats today, this morning. So the next thing will be to introduce our speaker today. So I think right now we need to focus more on our speaker. So I'll go off the camera here. So I believe he's online with us. Yeah, he's online with us. So without wasting much of our time, I would like to introduce Hamid Abdulsalam. Hamid is the lead data scientist at Factual Analytics Nigeria, based in Lagos. His research interests include statistical inference, statistical computing, machine learning, and deep learning. Hamid received his master's degree in statistics from the Ahmadu Bello University Zaria and a bachelor's degree in statistics from the University of Nigeria in Nsukka. Hamid is one of the first founders of our user groups here in Nigeria, specifically Lagos R User Group. And he's also an advocate of the use of R in both academic and the professional field in our country here. He has mentored so many students. Excuse me. So he has mentored so many students and professionals in the field in our country here. So having known Hamid, he's down to earth and he's very, very open in such a way that when he relates with you, you know that this guy, this is where he's going, or this is not where he's going. He's that open. So, and on his spare time on DataSum, Datasium.com, he blogs about data science and analytics. I have so much to share about him, but I will restrict that today so that we can use much of the time well. So I'll let him go into what he loves to do most, that's teaching and mentoring people about data science, especially using R. So please join me to welcome Hamid Abdulsalam as he takes us through machine learning using tidy models package today. So from our discussion I expressed his fear that, okay, the time might not be enough. So we're looking forward to extending this webinar to another month. So we look forward to still getting you all. So whatever you can cover today, we're ready. We are going to be appreciative of it. Thank you so much, Hamid. So I would like to welcome you in while you start. Hamid, are you there?
Yeah, good morning.
Yeah, good morning. So let me stop sharing.
Okay.
So you can share your screen now. Thank you so much for honoring us. Thank you.
Okay. Let me share my screen anyway. I'm coming.
Let me. Okay.
Sorry, good morning, everyone.
Yeah,
Hello?
we can see your screen now.
Okay. Can you hear me?
Yes, we can hear you.
Good morning. Okay, good morning, everyone. So today I'll be taking us machine learning with tidy models. And before we go into the discussion proper, this will be the program outline for today. I will introduce us to the basic concepts in machine learning. Then we'll look at some machine learning models. Then we'll go into the package itself, which is tidy model package. Then we'll apply the major packages inside tidy model. We'll apply it on a case study, which is the case study is Pay France Bank. Then we conclude about the whole thing. So let's go ahead and. So about myself, I'm the data scientist at Factor Analytics here in Lagos. Like Mrs. Baliki said, I have a master's degree in statistics at ABU Zaria and a BS in statistics at University of Nigeria in Nsukka. So my research interests include statistical inference, computing, machine learning, and DL. You can contact me via this email if you have any questions for me. So what was machine learning? Oftentimes we'll be hearing about machine learning. A whole lot of us is like, there's a new buzzword outside there now. But it's not just, machine learning is not just statistics. It's a field of study at the intersection of statistics and computer science. So it combines statistics and the programming computer science to solve problems. So it focuses on creating algorithms that can be applied on data sets in order to detect and exploit patterns. So the whole goal is for us to train model that we can easily apply on a new data set that will give us what we are interested in. So the core of machine learning is like you are trying to create an algorithm that you can apply on a data set, and at the end of the day, to do the automation for you, make the decision for you without you being there. So the primary use case for machine learning in business is to support decision making, in which data scientists attempts to discover and exploit patterns in data sets. Many machine learning models were developed from statistical learning. Others were developed independently. But in machine learning, model interpretability is not always an issue. What our goal is to be able to come up with a model that can accurately do what we needed it to do. So accuracy is a major issue for us in machine learning. Unlike in statistical learning, in statistical models, where okay, fine, you want to be able to interpret the models you are fitting. Most of these machine learning models are black box models, meaning that they were created to be applied. The internals of the machine, the algorithms, are not known to most 99% of data scientists. So most times the basic models are easily known, but as we move towards the complex models, what you need to do is just apply. But now with the advances in machine learning, like line packages and others, we're able to interpret some of the outputs here. But initially at the beginning of machine learning, it's all we needed is just apply the model, get the accuracy. But now most models now, at least with packages that are coming up, we're able to interpret some of these complex machine learning models. So the major difference between statistical models and machine learning models is like, in machine learning models, what you're interested in is prediction accuracy. Accuracy is our goal. Why in machine learning, in statistical models, you want to be able to explain your model. So in a machine learning, it's often common to make use of black box model whose internals are not fully known. Like I said, black box models are models that are actually complex, whose internals, how the algorithms are being used and all of that, and as in the mathematics behind the algorithms are not fully known. In a nutshell, machine learning model focuses on predictive accuracy over explanatory power. But there are two major problems in machine learning that we often use machine learning models to solve. The first problem is regression problem. Take for instance now, I may be interested in predicting the income of people based here in Lagos, let's say in Nigeria. Income is a numeric variable here. It's a number. So it's either you are earning $20,000 or it's a number, it's an income, it's a value, it's a numeric value. So that kind of problem will be solved using a regression problem because my target variable, what I'm trying to predict there is a numeric variable. But in a classification problem, what we are trying to predict is not a numeric variable. We are trying to predict a categorical variable. Take, for instance, I may be interested in predicting whether a particular customer will default on loan or not. So default here can either be you default, the loan status can either be you default or you didn't default. So that kind of target variable is a categorical variable. So when you have a categorical target variable, the problem you are trying to solve is a classification problem. So that's the major two problem we are always trying to solve in machine learning. So there are different types of machine learning models outside. I hope I'm not too fast anyway. Hello?
You're not, sir.
Okay. There are different types of machine learning outside there. So we have the supervised machine learning model. 99% of the model, you'll be seeing on machine learning are supervised machine learning model. So what's supervised machine learning model? In supervised machine learning model, we are actually trying to predict a target variable. So is either we are trying to predict income, whatever your problem is, we are trying to predict a variable. There's a target variable. We have a target variable we are trying to predict in supervised machine learning problem. In unsupervised, we are not trying to predict a variable here. We are trying to group similar items, similar observations together. So what we are trying to do is more or less like cluster here. We are trying to identify similar observations and group them. So it's often used in customer segmentation, whereby you want to profile customer based on their spending habits or based on whatever they are purchasing also. So in that situation, you are grouping similar customers based on certain metrics you want to use. So that's the major difference between supervised and unsupervised. So, but sometimes we may want to do supervised and start by doing unsupervised, by trying to create. So it's not as if every time you just do supervised. Sometimes you may want to group your observations, create a variable, perhaps create a new variable that can actually maybe a cluster variable that will group your observation based on certain metrics, then perform supervised machine learning model. So it's not as if unsupervised machine learning model can always be a way of you trying to explore your data first, do some feature engineering before you go down to doing supervised machine learning. Or perhaps we can just do cluster analysis if you are not interested in predicting any target variable. But the difference between unsupervised and supervised is in supervised, you have a target variable you are trying to predict. While in unsupervised, you are just trying to do a clustering analysis or trying to group similar observations together. Then we have the semi-supervised machine learning model. What the semi-supervised machine learning model does is it combines the label and unlabeled data. So take, for instance, now in unsupervised machine learning model, you don't really care about the labels anyway. What you're trying to do is you are grouping similar objects together so that you can identify what's going on. So what semi-supervised does is that it combines the concept between the supervised and unsupervised machine learning model to be able to come up with a machine learning model that will do your analysis for you, but it's not often used. It's not widely used among data scientists. So oftentimes you don't see semi-supervised machine learning models outside it. Then there's what we call reinforcement learning. In reinforcement learning, an algorithm is created to learn a policy for interacting with an environment in such a way that it maximizes a predefined objective. There's an objective set up for the algorithm. So what the algorithm is trying to do is to make sure that it maximizes that objective. A popular software that was built, a popular game that was built using reinforcement learning is the AlphaGo. AlphaGo is, the moment people started saying that AlphaGo was successful, then we started seeing a lot of research in reinforcement learning. Prior to AlphaGo, it was not really explored. Reinforcement learning was not really explored like that. So AlphaGo is the first computer program to defeat a professional Roman Go player, as well as the first to defeat a Go World champion. So it's widely regarded as the strongest Go player in history. So you can read a bit about AlphaGo, but it was created using reinforcement learning. Now, let's look at machine learning models. There are numerous machine learning models. Definitely, there are. If you go to tidymodels.org, you see a whole lot of machine learning models. AdaBoost, SDBoost. There are a lot of them. Bayesian machine learning models and all of that. But the goal is not to cover the whole model. We'll be looking at 3 basic models here: logistic, decision tree, and these are models you can get started with. But when you understand how this model work, you can take the knowledge to other models and exploit them anyway. So there are numerous machine learning models out there that can be used in performing machine learning tasks. In this training section, we'll be looking at 3 ML models. They are logistic regression, decision tree, and random forest. Why are we looking at these 3 models? Because number one, we'll be doing a classification problem. Like I said, we have regression problem and classification. So our case study is a classification problem. I believe after the training, you can explore regression problem as well, but it's not that difficult to explore. Once you understand classification problem, you should be able to do regression problem as well. Now, let's briefly talk about these models. Logistic regression is used to fit a curve to data in which dependent variable is binary or dichotomous. Take, for instance, in linear regression model, it's always, let me just come up with, let me paint, let me see. So in linear regression model, we usually have something like, let's say we have alpha, our slope, or bx, x, something like this. So I'm not trying to bore us with mathematics anyway. So I'm just trying to come up with, explain some things in this model for us. So in linear regression model, we have something like this. But in linear regression model, our dependent variable is always numeric, either income, salary, and all of that. Why? Because number one, it is created to do a numeric prediction. But in logistic regression model, we can't apply linear regression model on you can't apply linear regression model on a dependent categorical variable. So take, for example, let's assume you have a y, a dependent variable that is either you default on loan, yes or no. And you're trying to solve it with a linear regression problem. It won't perform, it won't underfit, it won't perform as expected. So that's why we have to look at logistic regression. When you have a binary dependent variable, whereby what you are trying to predict is either a binary class, either yes or no, default or not default, I or income, whatever your target variable is, then the first thing you think of is a logistic regression model. Now, the logistic regression model has a probability form of this. Now, what you usually do is like when you fit your regression in R, when you fit a logistic regression in R, it's very easy to implement. When you fit it gives you your slope, your intercept, and your slope here. Now, by putting your slope and your intercept and all this here, you are this pi here is the probability value. Now, what it does is that when you have this probability value, then we usually set a threshold. A threshold is that if it is greater than 0.5, if the probability value is greater than 0.5, put it at class 1, the person defaulted. If it is less than 0.5, the person did not default. So basically, the probability value that you get here is what you use in classifying your target variable, whether the person defaulted or not. So please, you can read more a bit about logistic regression, because if I should start talking about logistic regression today, we won't be able to finish the whole thing. Then we have decision tree as well. Decision tree is like a flow chart. So it's very, very simple to implement as well. So what you usually do is like, for instance, let me just come down here. So in decision tree, let's assume we have these are variables we are trying to predict. We have, let's say, employment status. We have loan status, and let me add another variable. Let's say sex or something. So what it does is like, first of all, these are dependent variable, which is either you default on loan or not. Please don't mind my writing anyway. I'm trying to use computer to write anyway. So what we are trying to do is I want to be able to use employment status and your gender to be able to know maybe the person will default on his loan or not. So the first thing we do in decision tree is to be able to calculate, the first thing is to calculate our information gain. How many information do we gain from these independent variables regarding this linear loan status? So take, for instance, if the sex give us like 0.6, we'll pay 60% of the information about loan status from sex. And let's say we gain the information gain we gain from employment status is like, let's say 0.4. Decision tree model will start to split the tree from this sex. So first of all, it will split the tree from sex. So if you are male or female, then it will go ahead after the sex. If the information gain we gain after sex, it go ahead and split the tree. The next information gain is employment status. Then it goes after sex. It put employment status here, and we have notes. We'll explore it in the next slide anyway. So what we do is that in decision to calculate the information gain of our independent variables, as regarding to the dependent variable, the one with the highest information gain is where we start the splitting from. So information gain measures how well a given attribute separate the training samples according to the target classification. It is used to measure. It is used to measure a measure used to select the best candidate attribute at each step. So let's look at this. Take for instance now, the refund that at this particular place, it uses refund to split the tree. Then after refund, it goes to marital status, then the taxable income. Now, what this table is doing is this. We have these three variables: refund, marital status, taxable income, and we are trying to predict cheat, maybe somebody will cheat on tax or not. Now, decision tree first of all start to obtain the information gain from these independent variables: the refund, the marital status, the taxable income. So if, like for instance, in this case now, refund has the highest information gain, it started the splitting from refund. Then the next one that has the next highest information gain is the marital status. Then it continued the splitting from marital status down to taxable income. Now, at this point now, it has used all the independent variables. Now, the question now is this: looking at this test data now, we can now use this text data to know if we default on loan or on tax or not. This person here that we are trying to apply this decision tree model on, this person did not refund, is married, has a taxable income of 80,000, either in naira or whatever currency it is. Now, if we put this information in this decision tree that we've created, we want to know maybe the person will cheat on tax or not. So first of all, we go to refund. So the refund is low. That means we come down to no here. Then we go to marital status. The marital status is married. That means we are going down here. So meaning that if this person is, the refund is low and the marital status is married, then the person will not will not cheat on tax. The end result will be no. So what we'll be having here is no. Here are the question mark here. Do you get the point I'm making here?
Are we together? Let's get this response.
Yes, we are together.
Yes, we are together.
Yes. Thank you.
So basically, what this particular person here, obviously the decision tree model shows that this person will cheat. That's basically what decision tree does anyway. Now there's a model called random forest. We realize that when we fit decision tree, oftentimes it's overfit. Overfit in the sense that when we train it on our trained data set, because in machine learning, what we usually do is like we usually create trained data sets and test data sets. What we do is we train the model with the trained data sets and we apply it on new data set, which is the test. The test was not part of training the model. So we believe that since the test data was not part of training the model, the model should be able, it should not be biased. Like the test data should not be biased on evaluating the model. Because compared to we using the same data that we use in training the model to evaluate the model, we have an optimistic performance, thinking that our model perform very well. So what happens is that most times when we fit decision tree, we realize that it doesn't really perform on new data set as well. So what they try to do, expert in the fit, thinks, okay, fine. Rather than just having a single decision tree, why can't we have multiple decision trees that will be doing the prediction? Then at the end of the day, the prediction that each tree comes up, we take the majority of the votes. Take for instance now, that's what random forest is all about. Take for instance now, let's say we have in tree A, let's say we have 3 trees. So we feed the first tree, the second tree, and the third tree. So in our random forest, we specify the number of trees we want and the number of columns to be used in fitting each tree. We'll get to see that when we move forward. So what we'll be doing, random forest is just collective of decision trees, collection of decision trees, I mean. So here now, no, predicted no. This guy predicted yes. as our target variable, and this one predicted no. So the random forest model will pick the majority of the vote, which is no. So the random forest output become no. So what the end goal of random forest for us to be able to fit many decision trees so that we don't just rely on single decision tree giving us the prediction. So in random forest, we usually create a new data set from the original data set to fit our algorithm. So what we usually do is this. There's what we call bootstrapping in random forest. What we do is, for instance, when we have a data set, let's assume these are full data sets. So we'll create a new data set from this. Take for instance now, there's an M3 argument there. How many columns you want to use in fitting your random forest now? How many variables, each tree, how many variables should it be used? So we can say, okay, fine. At each of the tree, use 4 variables. So tree 1 we use it will randomly select 4 variables. Tree 1 pick 4 variables from our full data set here. This one pick another 4 variables. Then inside this tree, then we have the number of trees. There's also n trees, the number of trees to use. So we can say, okay, fine, we want it to fit like 40 trees. So number of 4 variables inside this our full data set fits like 40 trees. Then at the end of the day, inside this, there's what we call resampling. So it will take, like, let's assume we have 1 to 50 observations here. And each tree wants to pick like 40 observations or 30. So it will take, let's say here it takes observation, randomly select observation 1, observation, how do I write? Yes, sorry. So what it does is like each tree we do resampling, meaning that many observations will appear more than once. That's sampling with replacements. So it will go into this full data set, picks maybe 30 observations here, 1, 2, up to like randomly. Now it can be the second one maybe 9, the third one maybe 10. So like 30 observations, but 9 may appear twice, of 10 may appear like 5 times inside this observation for this fitting this first tree. Then it goes again and pick another 30 observation, use it to fit the second tree. So that's what random forest does. It randomly selects new observations, but these observations are done with replacement. That's bootstrapping. So we bootstrap the data by resampling the rows with replacement. Some rows will be repeated and some will be missing in the new data set. Now, there's what we call model performance in machine learning anyway. When we fit regression problem, it's easy for us to use mean square error, which means square error. Which means square error is like you taking the square root of mean square error. What that does is like, take for instance, let's assume we are fitting a regression problem now. Let's assume we fit a regression, a simple linear regression problem here, and we have maybe when we fitted our model gives us a slope of 4 point something, 4.7 as our intercepts. Plus. So let's assume we fitted a regression problem here. So we now have a new person whose age is, let's say, 30. His actual age is 30. Do you get the point? So we are trying to use it to predict his income. Our Y is income, our X is age. So our Y is what we are trying to predict with this linear regression problem. So, but we know his actual income. His actual income is 40. But we created a model thinking that, okay, fine, this is our model. Once we put out his age here and we do the multiplication and addition, it will give us a 40, like close to the value. But as when we fit this is age here into the model, and at the end of the day, the model predicted, let's say, 39. Now, the error now becomes the observed minus the predicted. The actual minus the predicted or the observed is same thing. Actual and observed are the same. So the actual is 40. The actual income is 40. So 40 minus the predicted, but the model predicted 39. So minus 39, our error becomes 1. So this error here now. So let's assume we have like 40 guys that want to predict their income. So we obtain errors for each of the 40 people that we want to predict their income. So this error is where we take the sum square error. There's a mathematical underground to it anyway. So here we take the root, the square, the error is what this error that I just obtained. We square the error take the sum of square error, then square it, then take the mean. That's what will give us the mean square error, then the root mean square error and all of that. So that's for regression program that I just did. But in classification, we can't use the same regression. We can't use the same mean square error, the metrics we use in regression to observe the performance of our classification problem. Because how do you take, let's say the target variable is either yes or no. Do you get the point? How do we subtract yes minus no when maybe it's predicted no and the actual is yes? You can't do subtraction here and take error here. So that's why at the end of the day, we come up with what we call confusion matrix. From the confusion matrix, we can be able to calculate our accuracy. The accuracy there is the true positive plus the true negative all over true positive, true negative, false positive. You will get to see that when we move to the next slide. Then we do the precision. Precision is the true positive over the predicted positive. We get to see that when we get to the next slide as well. Then there is what we call recall. Recall is the sensitivity. It's also sensitivity, which is the true positive that are actually predicted from the test observation. Then there's what we call area under the curve as well. All these metrics can be obtained from the confusion matrix. So let's look at confusion matrix. Now, this is the confusion matrix. How do we come up with a confusion matrix? Take for instance, let me just come up with this. Let's assume we have our target variable to be, let's assume loan status. Either you default on loan, yes, or you don't default, no. So let's assume in the real observation, the real data set, when we have the test data set, this person here defaulted on loan. This one did not default. We have this one defaulted, did not default, and let's say defaulted, yes, or something. Then the predicted, after fitting our model, we now try to use the model to predict our test data sets. We want to be able to see maybe it will actually help us to predict this the way they are. So the predicted, now we have the predicted. So instead of predicting this to be yes, it predicted it to be no. Instead of predicting this to be no, it's also yes. This one also becomes no. It's predicted this accurately, but this one it predicted it to be yes. This one it predicted it to be no. This one yes. This one no. So these are prediction, but this is the actual label. But when it predicted it, this is what it predicted. Now from this here, we can come up with our confusion matrix. What we do is that we have the actual here, and we have the predicted here. Now, we have either the yes or no. The yes is positive and the no is negative. And we have the yes like this, and we have the no here. Now, the confusion matrix is how many were actually yes that were predicted to be yes from our model. The actual observations were yes, but when the model predicted it, it's predicted it to be yes. From here, the confusion matrix, we count it. This one is yes, it predicted this to be yes, and this one was yes actually, but when it's predicted it to be yes. So the true positive here will be 1, yeah, it will count 1 for this. Then it will go to the second one. How many of the observations were actually yes, but when it predicted it to be no. So this one, it was yes. By the end of it, it predicted this one was yes, it predicted it to be no. This one is 1. This one was yes, it predicted to be no. This one is 2. Yes, and predicted to be no. This one is also 3. So we have 3 here. Then how many observations were no? But when it predicted it to be yes. So if we count this one was no, yeah, but it predicted it to be what? Yes, yeah. So this one becomes 1 as well. Then it looks at this as well. It comes again and look at the last one. How many were no in the original data set? When it predicted it, when the model predicted it to be no. Then it looks, this one it was no, I predicted it to be no, yeah. So I think we only have 1 here as well. So these are our 1 here is our true positive, yeah. And these are false negative. Why is it false? Because it is not a true negative. It was actually a yes, but it was predicted to be no. So it is a false negative. Do you get the analogy there? So it is not actually yes, but when it's predicted it to be no. So the negative here is false. It is not true. Then here as well, this place is no, but it's predicted to be yes. So this one is false positive here, because the positive here is false, because it is not a true positive. Then here we have 1. This one is a true negative, because it was actually no, but when it's predicted to be no. So this one is true negative. So from this now, we can now come up with our accuracy. accuracy here becomes these diagonals here, these guys here, the two positive and the two negative, all over the entire two positive, false negative, false positive, and two negative. So what we have here will be two positive plus two negative all over this entire thing, two positive plus two negative plus false positive plus false negative. So that will be our accuracy from here. So let's assume this model here, this prediction that we had here, we got this prediction from logistic regression model. This prediction is from logistic regression model. We'll do the same thing for decision tree. We'll do the same thing for the random forest. So let's assume when we obtain different convolution matrices for each of these models here. So let's assume when we obtain the accuracy for logistic regression, this one was 0.9. We obtain the accuracy for decision tree and the random forest. The one with the highest accuracy, if accuracy is the measure of performance that we want to use, the one with the highest accuracy will be the one we pick as the best model. Then there's what we call sensitivity as well. Sensitivity is two positive here, the proportion of the two positives that were correctly labeled, two positive here, all over two positive plus false negative. So this one here is our sensitivity from here. So, and also we have the specificity, which is the false positive and the two negative all over two negative plus false positive. So these metrics are obtained from the convolution matrix anyway. So that's what convolution matrix is all about. So these are the two positive, false negative, and all. So these are accuracy I just talked about, two positive plus sensitivity, which is also we call, which is the formula here. The precision here is targeted at the proportion of the two positive that are correctly predicted from the predicted classes. So the most commonly used metric is always the accuracy, which is obtained by dividing the total number of correct observations by the total number of observations that we have. Now, I haven't talked about convolution matrix, logistic regression, all of this. Now, let's look at the tidymodel package. Some of us were familiar with the tidyverse package. Before the tidyverse package, what we usually do is like, we do the data visualization, loading ggplot on its own. We do the data manipulation, loading the package for data manipulation, which is dplyr and all of that. So we load this package independently. But with tidyverse, they combine all these packages so that we can call it with just a single package, which is tidyverse. Same approach is used in tidymodels. Before tidymodels, what we usually do is like we load the caret package, we load the ROC curve package, we load different packages that we want to use for machine learning models. But with tidymodels now, instead of loading all these packages, they created a framework for you to just load tidymodels. So inside tidymodels, we have a collection of packages doing different tasks. Take for instance, now we have the parsnip package. That parsnip package is where your algorithms are sitting. So if you want to build a decision tree, you look for the engine where the decision tree model is sitting in the parsnip. So what you focus on in the parsnip will be the output. Let me just do some Googling here. Let's go to tidymodels. I think. So models. I'm trying to come up with a parsnip package. My internet is a bit slow. Apologies, man. So we'll come back to this later. So let's save time anyway. So what I'm trying to show you is that inside the parsnip package, we have a whole lot of different models. So when you are trying to fit a model, parsnip package is what you think about. Look at the engine where the model is sitting inside parsnip package. We'll explain that when we move forward. Then we have the arg sample package still inside the tidymodels package. The arg sample is used in splitting your data sets. So like I said initially, in machine learning, we usually try to split our data set into training and test data sets. So what the package that allows you to do that is a arg package, arg sample package. Then we have the recipe package, whichever pronunciation it is. That one is actually for data processing. What we usually do is that we don't just, when we split our data set into training and test data set, we don't just go ahead and fit our model straightforward. So because doing that will be tantamount to saying, okay, fine, we don't just process the data. So our data, once we don't process the data and we fit our model straight up, we end up having a model that will not perform very, very well. That will overfit anyway. Then we have the yardstick, which is basically for model performance. Like we want to see, okay, fine. After we've fitted our models, which of them has the highest accuracy, which of them has the highest sensitivity, precision, all those metrics that we are interested in. Then we have the dials for model tuning. Basically, we don't just, because most of all these models usually have more than one parameters. So we want to tune those parameters. How many number of trees should we use? Like in XGBoost, we want to see, okay, fine, what's the minimum observations, the depth of the tree and all of that. So many parameters comes with these models. So when we want to tune those parameters, use the DAS package. So in this training, we'll be looking at these packages as we move forward. Now let's look at the case study. Before it is always good to apply these things what we ever learn, what we are trying to, this tidymodels package on a case study so that we can be able to understand what's going on. So we want to explore the tidy package on a case study. So let's assume you are a data scientist with Papers Bank. Papers is just a fictitious name I created anyway, with Papers Bank analytics team. So during the COVID-19 pandemic, many people banking with Papers may find themselves in financial difficulty, unable to make loan or credit payments. So Papers Bank is currently looking for methods to assist its loan clients who have been impacted by epidemic and its economic consequences. So Papers Bank will aim to develop a predictive algorithm to identify loan clients who are mostly likely to be in financial trouble. So what they did is they completed the data grading effort. They just completed the data grading effort to track their clients' financial distress condition. They had a database of previous clients that were in financial distress. So using those database, they want to come up with a predictive model so that once they have this, when they come up with that model for a new new customer, by putting certain variables in that model, they should be able to know whether you are in financial distress or not. The model should be able to tell them that, okay, fine, this person is in financial distress or not, contact this person. So that's what they are trying to do. So Paper intends to utilize this information to conduct a target campaign to identify most at-risk loan clients and discuss potential strategies with them. This is because by finding and providing acceptable choices for this customer, Papers may be able to reduce the projected loss from them as compared to a scenario by they fail to declare them and allow them to default. So we have a database, a historical record of customers who were previously, we know their financial situation, whether they are distressed or they are not distressed. Now, but we have a new customers who we don't know whether to label them as distressed or not, but we have certain variables about them that were common with previous customers, but we just don't know the current state of these new customers that we have. So using those previous data that we have, we can come up with a model. By using that model, by creating that model, we can apply it on a new data set that we just have that will actually help us to accurately predict if this customer is in financial distress or not. So Papers, on the other hand, will prefer to limit interaction with loan customers who are not financial trouble in order to prevent giving supervision. So they don't want to say about, okay, fine, by just doing guesswork, just targeting a customer that is in financial distress. And you know, when someone is not in financial distress and you label the person as being in financial distress, that means you'll be spending extra money because at the end of the day, that's one classification. So they want to be able to come up with a model that can accurately help them to do the prediction. So you've been given two data sets. The first data set is titled campaign. Is the process data, which includes the financial distress status of 5,000 loan customers. That's the first data set, which is the historical data. Then you have been instructed to create an accurate machine learning model based on this data in order to identify low customers who are likely to be in financial difficulty. So the second data set is the new data set that you want to apply this model that you've created on, which is a data containing 3,000 loan customers. So this is data dictionary anyway. This is variables, the loan status. So it can either be you are in distress or you are not in distress. Then we have the loan amount, the purpose, the income, and all of that. So I won't spend time on this data dictionary. We can read this up later. So let's switch back to our R. So I'll be starting from this part here. So this part here, we imported the data set. So yeah, what I did was like the grid extra package allows me to have a multiple plot on a single plane. So instead of me having 4 different plots showing on different pages, I can combine these 4 plots on a single plane. That's what the grid extra package does. Then the tidy models, like the tidy models is what we are trying to use to build our machine learning models. And the tidy models, like I said, is a collection of packages that allow you to do different tasks in machine learning model. Then we have the tidyverse. I don't know, maybe many of you used tidyverse package before. Tidyverse allow you to do data manipulation, data visualization. We have like 6 or 7 packages inside tidyverse. We have the dplyr, the tidyr. So definitely when you are building and when you are doing most times, 99% of them when you are doing analysis in R, you always want to know the tidyverse package because that's where you do most of your data cleaning, data manipulation, and all of that. Then we have the cable extra. Cable extra is just allow me to knit my table. You don't really need it for now. It's just allow me to put my table, the output of my table in a proper form. So yeah, we are learning the data sets. Yeah, I believe we are used to this code before. If we don't, this part here is just reading a CSV file for me. So I want to read the CSV file inside my directory. So this is the directory I'm working on. Think or something. So this is the directory I'm working on. So inside this directory, I have a data called campaign. Where is a campaign here? So this is the data here. So I'm saying go to that directory, go to that part, load this data for me. I'm interested in the header as well. Then string as hello? Hello, are we here?
Yeah.
Okay.
Sorry for those who are joining us. I shared the file for this webinar in the chat box. Please confirm if you can see so that you can follow along with the code and run it, then you can ask questions. Thank you. So you can go ahead, Hamid.
Okay. So this part here is just me saying, okay, fine, we needed the string as factors. If I remove this part here, it will load them as character. The factor variable they will be seen as character. And we are not factor, they are not character, they should be seen as factors. That's why I assigned this to be true. So if you do this, it will run for some seconds. So it has loaded the data set here. So most times when you bring in data set into R, you want to glimpse your data, you want to see the structure of your data set. So I could use structure, I could use glimpse inside the tidyverse package. So yeah, I'm saying let's use SQL structure here. So I'm looking at the structure of my data set. We look at this data set, we have an ID variable, which is also an identifier, trying to identify each customer. So you won't be using your identifier because it's not going to play any role in your model, in your model building. Then we have our data variable, which is loan status. Now, if you look at the data type for the loan status, it's seeing it as integer. Integers are just whole numbers. So we have to work on this loan status there because it's supposed to be seen as factor. Where is zero is either you from our data dictionary here. If you look at our loan status, our loan status says that 0 is not distress and 1 is distress. So we want to make it to look at either not distress or distress. So we'll be fitting that in the next slide. Then we have other variables that are factors. So loan amount is either your loan is high, your loan amount is high, low, or medium. So they have a way of classifying your loan paper, your loan purpose, the income, and many other, the employment length, and all of that. So this is just we are storing our data set. So our type variable loan status is seen as integer. Let's convert it to factor and assign level names. So yeah, what I'm doing is that go to because my data set, when I brought it in, I call it DT. So I said, go to the DT data set. Inside it, access the loan status variable, then convert it to factor for me. So this part here, to convert it to factor, factors are categorical variables in R. So if you convert it to factor, that won't be seen as integer anymore. So after converting it to factor, each of the levels there now, the first one is 0 and 1. So assign not distress to the 0 and assign distress to the 1. So that's what this part here is doing. Is it understood?
Yes.
Yes, we are following.
Okay,
Yes,
so this,
I'm
okay,
following.
okay, this part here, what I'm doing here is, okay, fine. I want to check for missing value. So the code sum function allows us to check the number of missing values. So its NA is like, we are asking, we are looking, is there missing value in our data set? This is NA return either true or false. But the code sum, we count the number of two inside the is NA and come up with the number of missing value for us. So when we do this here and we come down, we realize that we have no missing value in most of our data sets. But this debt to income joint has like 437 missing values, 4,732 missing value, same as this income joint here. So, and region also has 1,034. Now, the issue now is this. I can't just say delete all the missing values. If I delete all the missing values, that means I'm deleting 4,000. We have only 5,000 data sets. That means I'm deleting 4,000 for almost like 90, more than 90% of my data sets will be deleted. Then which data will I use to do the modeling? So what I'll be doing now is this: I only remove these variables because I can't do imputation, because if I should input data, let me just, okay, fine, let me replace the missing with the median or whatever thing I want to replace. How am I sure that I'm doing the right thing with the median? So imputation sometimes is just, it's not always accurate. So the logical thing to do here is to remove these two variables, because majority of its values they are missing. So we'll be removing these two variables, but the region, I can still cope with region, meaning that, okay, fine, if I think region can play a role in our model building. So rather than removing the region as the data set, I can just remove the missing values in the region and go ahead with the remaining data set to find model. Because when you remove missing values in R, what it does is that it removes them by rows. Take for instance now, let's say this is row 1. Let's say this is row 1, and we have column 1, column 2, column 2, and value here in column 3 is missing. The entire row will be deleted. So, and I don't want to do that here. So that's why I will only remove these two variables, then we'll remove the missing values in. So this part there, 95% of the Brazilian in this income are missing. Hence, we will delete these variables. 20% of the Brazilian regions are also missing. We'll remove these missing values. So here is me removing the ID variable in the data set. We don't want to use the ID variable to do anything in our data set, like I said initially. Also, me removing this income joint and this other one, setting them as null. Then after that, help me to drop all any other missing values in my data set. So what we'll be having, if you do number of rows, n rows now, n rows dt, what you'll be having should be 4,000 or 3,000 something or so. So I'm having, sorry, n row, sorry, should be n row. So I'm having like 3,996. So this 3,996 is what I'll be using fitting my model after I've removed the dropping missing values in our data sets. Now, the next stage is data exploration. Oftentimes, it's always good for us to explore our data. It's not as if we are solving any problem here yet. In machine learning, we just explore our data and see what insights we may be seeing. For instance, if you have a numeric variable in your data set, and most of the values in your numeric variable are skewed to the right or skewed to the left, you want to take the log of, because most machine learning models don't really work very well with skewed data sets. So what we do is we take the log to balance the skewness in our data set. So, but how do you see whether your data is skewed or not? It's through data exploration. Also, in our categorical variables that we have, we want to see how distributed they are, whether they are broadly distributed or one is skewed or they are not broadly distributed. So that's the question you are trying to get from your data exploration. So it's not as if you are trying to fit a model, you are solving a problem, and here you're just attempting to see what is going on in your data set. So we'll be using ggplot. Now, when you are using ggplot, what it does is like you call the ggplot function and you go to the data, you ask the data, you go to the data set. The next thing you create your statement. Hello, I'm with you.
Yeah, sorry to interrupt you. Please, is it
Okay.
possible that you can share the script with us via the
Okay,
chat?
can I send it now? Let me just say it now. Yeah.
Yes, thank you so much.
Okay. So I've sent it.
Thank you so much.
Okay, so what we have now is this. We're just in ggplot. Normally, you call your ggplot function, and then you call your data set, you do your mapping. Your mapping now depends on the kind of plot you're looking for. If I'm looking for a scatter plot, that means I'll be having X and Y, which are two numeric variables. They must be numeric variables. Or if I'm looking for a bar plot, I'm only having it, unless I'm looking for I'm doing a multi-class bar graphs. But even if I'm doing more multi-class bar graph, what I'll be doing there will be filling in the aesthetics there. So I'm having a single bar graph here for a single variable. So even loan amount as my X, yeah, then plus in ggplot we use the plus from the plus symbol to say what next we want to do after we've done the previous step. So this plus here is saying that assign title to my model. The GG title here is the loan amount, as a title for the plot is loan amount. Then the x-axis, the label for the axis is loan amount, and I'm looking for a bar graph. So here I'm saying, okay, fine, give me a bar graph here. Then called flip the x and y axis. So I don't want it to show the x-axis on the x. Flip it. Let whatever showing on the x-axis to be on the y-axis, so that based on the fact that I want to be able to see the labels very well. So if you want this here, it will on like this, then you come down. So like I said, I told you about grid extra the other time. This grid arranger is inside the grid extra here. So I'm trying to put these two plots here, P1 and P2, trying to put them in a single plot so that at least I can have them instead of showing them at once. So if we play this here, it will show us our plot. So what we are going to see is that as far as loan amount is concerned, the median happens to be the highest occurrence here, while the low and high seems to be not really far from each other. As well as if you come to the loan purpose, the purpose of collecting loan, as far as most of this customer is concerned, is basically debt consolidation, which is the highest bar showing here. So what you're just saying is that you're just talking from your, whatever you're saying, you are picking point from it. You're just trying to explain what you're seeing from the graph. So like for instance, some of like loan purpose now, it's not well balanced because most of it is it's close to the debt consolidation. Most of it is on debt consolidation. At the end of the day, we'll be turning most of these categorical variables to dummy variables. I will explain what dummy variable is as we move forward. So the insight we are seeing here is that loan amount, most of it are in the medium part, while the low and high are not so close. Why? Same thing, loan purpose seems to be the major collecting loan. Same thing, we do the same thing for income, debt, income, application type, and region. So I won't spend more time in explaining the bar plot because you can see whatever's happening from the output there. So what we needed to see is to see if they are broadly distributed or not. Like this one now is broadly distributed. Now they are evenly distributed here, but application type is not evenly distributed. Like most of it are on single, while joint is very, very low. So most application is definitely single. Same thing, income is medium, low, and so we are just seeing insights from the data set. So I won't bother much in explaining the same thing, home ownership here. You can see that order is very, very low, but recent inquiry is evenly distributed, but others are not evenly distributed as well. And lastly, I think we have this. So we have past bankrupts and credit utilization, delinquency. So most of these are not evenly distributed, while others are evenly distributed. So loan income, region, all of that are widely dispersed. The following variables are not widely dispersed. But I haven't seen that most of our variables here are categorical variables. Machine learning models work very well with dummy variables. So what we'll be doing in the next step is for us to process these categorical variables so that at least the machine learning models can handle them very well. Machine learning models like XGBoost and all of that don't work very well with just factors. You will like putting them in dummy variables. So this next slide is we trying to set seed and trying to divide our data set into train and test the data set. The set.seed is just for us to be able to have consistency in our outputs. Take for instance, now if I should run this code with another sets of seed, my value for acquisition of that may be slightly different from somebody who uses 10,000. So 10,000, this sets of seed, once you set seed in R, just for reproducibility, just for you to have constant result, like uniform output as we move forward. So this part, initial split here, like I said, I talk about the out sample package in the tidy model. The out sample, the initial split is found in the out sample package, where we are trying to split our data set into two proportions, the training and test data set. So what this function there is, go to my data set I brought in, which is the DT, divide the data based on this proportion, 70-30, which is the largest size will be the 70 and the smallest size will be the 30. Now, the trainings, as soon as we've done the division here, assign the training data set to the largest sample, the testing data set to the smallest sample. So automatically, when you the training and the testing function in this initial sample, when you call it on your split here, it automatically assign the train set and the test set. So we've split our data like this into the training and the test sample size. Now, there's what we call data processing. So we don't just want to, like I said, we don't just want to fit our model like that. Following the division of the data set into training and test sets, the next step is to pre-process data before modeling. Data processing is frequently performed once our data has been divided. At this point, we will convert our categorical variables to dummy variables and set and scale the numeric variables, because many machine learning algorithms operate best with dummy variables. So what we are trying to say with center and scaling is this. Like what I mean by dummy variable. Take for instance, now, when you have a variable like, let's say, sorry, let me create a new split. When you have a variable like, let's say, sex, and you want to convert it to a dummy variable, we have either you are male or you are female. So what it will do is like, let's say we have like 3 females and 2 males. What you do is male becomes a new column, female becomes a new column. So here now, male is yes. So this case will be 1 under, this one becomes 0. So it's a value of either 0 and 1. These two become 0 because they are this under this male, they are not male. So this one becomes, so I've turned this sex with dummy variable. Same thing here, this one becomes 0, this one becomes 1, 1, 1. So that's dummy variable. So this part here, we are converting them to the categorical variables in our data set to dummy variables of 0 and 1. After we've converted them to 0 and 1, then we scale and centralize it. Centralizing is you are trying to subtract each values from their mean. So when you've centralized, then you want to scale them by subtracting it from their mean, then dividing by the standard deviation. So that's what centralizing is all about. So yeah, we'll move forward and say, okay, fine. So like I said, we'll be using the recite package in tidy models. So what the recite package does is like, first of all, you specify your model, the pre-processing steps. You specify it. It will be in terms of formula. So from once you've specified the specification, as in the model formula, then you make a preparation. You talk about the steps you want to take. You identify the steps you are interested in. Once you've talked about the steps, then you prepare it. Oftentimes you prepare it on the train test. Once you've done the preparation, then you call the bake function. The bake function now is, okay, fine, all these steps that I've highlighted, let me to bake it on the train and the test. So the bake function is what we now apply all those steps and prepare them on the test and train data sets. So let me just show you here. So what we are trying to do is this. Here you are specifying, we call the recipe function, and we are specifying our formula here. We said our loan status is depending, when I say see that dot here, I mean that it's depending on every other variables in the data set, because every other variables they are independent variables, except the loan status. Then we say, okay, fine. The data we are using is the train set. Remember, we split the data into train and test set. So we are trying to do the preparation on the train data set. So this pipe function here is pronounced as then. Is always pronounced as then. Okay, fine. After this, then do this. That's what the pipe do. So after we specify the recipe, then step dummy. We are trying to convert, like I said, the dummy variables. All the nominal predictors. Nominal predictors is like all the independent variables that are categorical variables. Help us to convert them to dummy variable. But one hot code is like all the levels there, because all this, without putting the one hot code there, it will not retain the reference levels. It will turn every other variable to dummy variable, every other levels to dummy variable. But the reference one will not be turned to that. So one hot code is just for us, okay, fine, including reference in the level, in every levels in the predictors. convert it to the dummy variable for us. Let's see them on each column. Then the step center, once it has converted to dummy variables, now those variables now becomes values, it becomes numeric of 0 and 1. Then we say, okay, fine, centralize it, subtract each value from the mean, then scale it, divide it by their standard deviation. Then after you've done all this, prepare it on the train set. So this preparation is just that we specifying the step to take. It's not as if it has done anything yet. It's just, okay, fine, these are the steps that we take, but I have not applied the step yet. So these are what this part does. Now, after we've specified the steps we needed, then we call the bake function inside the recipe package as well. We bake the steps now. We bake it now. So, okay, if I help us to bake all these steps now, all these steps we've mentioned, bake it on the train set, apply all these steps on the train set. So it will convert, it will go to the train set and convert the nominal predictors, numeric predictors, to scale them and centralize the way we wanted it to do. And as well, don't just, because we know we are working with two data sets, the train and the test. Don't just bake on the train alone, bake on the test data set. That's what this pre-processing does here. So when you want this one runs like this. Any question here? Okay.
Okay, at this point, if you have any question, I think Hamid would love to pause here and take some questions. Do you have any questions? Let's take that in the next 5 minutes. You want to put it in the chat box, or you want to say that you're free to choose? Okay, we have one question here in the chat. So Jawad is asking, what is the difference between test and training data?
So, okay, fine. Very good question. So the major difference that I'm saying now, take for instance, let me come up with my paint here. Sorry. So we have something like this, data sets. I'm sorry. So let's assume you're given a full data set. You're given a full data set here. This is my full data set. Full data. The client gives you a full data set and he wants you to come up with a predictive machine learning. In our normal statistical approach that we usually do prior to machine learning and all of that, you want to fit, let's assume you want to fit a logistic regression model or linear regression model. You fitted your logistic regression model on this entire full data set. You fitted the logistic linear regression model on this. Now, this same full data set, you want to now see the performance of your linear regression model. You now use this model that you obtain from this full data set. Use this data set to still evaluate your model. At the end of the day, maybe you're having 0.99 adjusted R-square, which is 99% adjusted R-square, and your mean square error is very, very high and all of that. Like your model performed very, very well. I mean, so at the end of the day, you get to realize that your mean square error is very low, your adjusted R-square is very high. You realize that your model performed very well on your full data set. Now you're not giving a data set that is not part of the full data set, like a new observation. Because the essence of building a model is for you to be able to apply that model on a new data set that you've not seen before. So now you apply the model on your new data set, and at the end of the day, it helps you, it performs very woefully. Now that's the problem with training and test data set. We realize that when we apply a model on the entire data set and we evaluate our model, we usually have optimistic performance. Our data set, our performance is always high. But when we apply that model that we created using our full data set on a new observation, it overfits, meaning that it performed very well on our original data, but on a new observation, it performed woefully. So now the concept now is, okay, fine. Let's come with this full data set. Let's divide it into two. Let's have the training and let's have the test. Now, the training now becomes, okay, the training now, these are data sets, divide it, make the training to be 70% of our full data set. And the test become 30%. So what we are doing is that this entire full data set, we divide it into two portions, the 70 and the 30. Now, mind you, it's randomly assigned values inside this 70%. Now, let's assume this entire data set is, let's say, 5,000. 5,000. Then 70% of 5,000 here, let's say it's around 3,005 or something or so. So this one is 3,005, and these are test data sets will be 1,005. Now, at the end of the day, we cannot build our model on these our training data set. We use our model to train, we use our training data set to train our model. So there's what we call cross validation, although we won't be covering cross validation inside this part. Cross validation is like we may use the number, depending on the number of folds you are interested in. You may use 3K fold. K fold is like how many Ks, how many folds. You may use 4 fold, 5 fold, depending on the number of folds. But yeah, let's assume you use 3 fold cross validation. You train your model on this training data set. So whatever the performance of your model is on this data set, you don't want to evaluate the performance of your model on this training data set. You want to evaluate your performance of your model on this training data set. Now, remember this test data set, remember this test data set was not part of the data used in training the model. So whatever performance your model is on this test data set is the actual performance, because it is not the same data that we're using in training data set. So whatever the performance is, which will give you the idea how your data, how your model perform. So when you now see a data set that is not part of your full data, that is a new data set entirely, and you want to apply your model, at least you'll be sure how your data set will perform before deploying it to the web or deploying it to any application that you want to use the model for. So that's the train data set. The train and test data set is just for you to train your data on the train data set, evaluate the performance on the test data set before you deploy it on a new data set that were not part of your training and test at all, so that you can see how your data performs. Have I answered that question?
Hello, Jawad. Okay, yeah, he said thank you. I think that's answered.
Okay.
So we have somebody raising their hands. I think Oluwa Femi, I think you were raising your hands before.
Very much. Morning. Good morning, sir.
Okay, good morning.
Okay, thank you very much for a good presentation.
Okay, sir.
My own concern here, I want to ask, because when you were talking about the model tuning, you made mention of the dial package will be used for tuning. So I want to ask, what about, because I know in tidymodel, we also have the tune package. Can we also use the tune?
Why not? You can use the tune as well. Definitely.
Okay, and also, what about in a case you are trying to fix you have a classification problem in which you have a class imbalance? Because I saw from the slide you were showing when you were doing some visualization with the bar graph. So how do we go about that in case we have a class imbalance?
So basically, when you have class imbalance in machine learning, what we usually do is that there are a lot of steps we use in creating during the class imbalance, because it's a major issue in machine learning that I always. But what I usually do is that I don't rely on accuracy alone to take my measure of, to use as measure of evaluating my model. So that's where I come from. Kappa, I don't know Kappa. Kappa treats the accuracy based on the class imbalance. Do you get the point I'm making? So when you know that your data set is imbalanced, so the measure of metrics you use should be likely dependent. You don't just think of accuracy as a measure of accuracy. The class imbalance there, the accuracy that the measure of evaluation that I use your kappa accuracy to pick your variable. Although there are also techniques that we use in fitting to make sure that the data remains imbalanced by making sure that, okay, fine, those that are not balanced in the test data set or the training data set, we make sure that, okay, fine, we create some models that will input more other balances, but those measures are not, like in machine learning, those measures are not always accurate. So definitely class imbalance is still something that they are still being researched upon. But what I usually often use that when I have a class that is not imbalanced in my data set, rather than using accuracy, I use kappa as a measure of accuracy to pick the best performance, because it takes into consideration the imbalances in the target variable. Do you get the point I'm making?
Yes, thank you, sir.
Okay. Any other question, please?
I think you can go ahead at this point. We'll take other questions maybe later. Thank you.
Okay. So we've baked the data set, we've done the pre-processing. Then let's look at the modeling here. Now, in tidy model, using the PaySnip package, the first thing you do is just you specify your model specification. Take for instance, if I'm building logistic regression model, I start with the logistic regression specification here by creating this. Like, okay, fine. I want to create a logistic regression. I want to create a logistic regression model. Sorry, excuse. I want to create a logistic regression model. Then this pipe function is saying that then what's next? Then there are a lot of engines. If we go to the, let me see, there are a lot of engines there. Let me go to the page, the tidy models. Please, sorry. Looking at the engines. Perhaps I'll check that later. So I'm trying to show you the engines inside the PaySnip project. But there are a lot of engines. Maybe I didn't get the site very well. So there are a lot of engines inside the PaySnip. So for instance, like the engine for logistic regression is GLM. There's also GLM.net. You can pick your logistic regression there. If I'm doing random forest, there is an engine called Ranger. You can use Ranger. There are also different engines. So if I'm doing the decision tree, the engine I use is outpath. Depends on the model you are trying to fit. There are a lot of engines inside there that you pick your model from. So yeah, I'm saying, okay, fine. When you be picking the engine I'll be using for this my logistic regression is the GLM. Yeah. So for every of the model you are building, this particular part is very, very important. Then you specify the mode of the classification. The mode is like the classification problem we are trying to solve here is a classification problem where you're trying to see if somebody is distressed or not. So the classification, the problem here is classification. Then we fit the model. So these are the steps we identify. There is no parameter to be tuned in logistic regression model. So we don't specify, and we are not specifying any parameter yet. Then as soon as we've done this, when we play this, we fitted the model like this. So yeah, we fitted logistic regression number on our training data set. We start by creating the logistic model specification log reg. Then we set the engine to GLM and mode to classification. And we finally fit the model using the fit function. That's the steps for PaySnip. Then now I'm trying to do the same thing because we are trying to fit three models now. I'm trying to do the same thing for decision tree. So I said, okay, fine. Go to the decision tree. I'm specifying the decision tree as my model specification. Then, like I said, the engine for decision tree is outpath. I'm solving a classification problem, which is either you are distressed or not. Then I fitted my model. Yeah, my dependent variable load, depending on the rest of the variables in the data set. Theta dot here, meaning that the rest of the variable. Then the data is the baked train on the train data set, the baked train data set. So when I do this as well, it runs the decision tree model for me. Now, same thing here, random forest. Now, I'm trying to fit a random forest, but I'm using 5 number of variables to be used for each splitting. So I want 600 splitting. This is arbitrary. You can work around this number of splits depending on whatever accuracy you use. For example, if you have an accuracy of 0.6, you can increase the number of trees and maybe to increase the accuracy anyway. You can work around the number of trees. There is no lay down number of trees that you must choose anyway. But that's a parameter when it comes in anyway. So the number of M3, the rule of thumb is that we use the square root of the number of observations. So if you are confused on the number of M3 to use, you can just take, if I have like 20 or 25 variables columns in my data set, I can just say square root of 25 observations. That will be 5. So my M3 will be 5 here. Now, the engine I'm using is the random forest model that I'm trying to build is sitting inside Ranger. So I specify my engine to be in Ranger engine. Then importance impurity. Basically, okay, fine. If I needed to do the variable importance, that will be the use impurity as variable importance for me. Then set the mode to be classification. Then fit the model. So yeah, same process. We do this. So we utilize the decision tree function for decision trees and random forest function for the random forest. They're also used for various, they're also from various engines, and we have varied parameters in the random forest. For example, we use two parameters, M2 and M2 number, the trees. So here we are just building 600 trees, 5 columns, 5 variables to be randomly selected for each trees. Now, I haven't done this part here. We've fitted the model. Now let's evaluate our model here. But we can't evaluate our model without predicting first. So here we want to predict the performance. Want to build on our test so that we can now see how it performs. So the bind columns there is just binding two columns together. So that we can have the actual and the predicted. So that's why we are trying to use the bind column. Then the select, like the select is inside the dplyr, which is part of the package is loaded inside the tidyverse. So I said inside the baked data set, pick the loan status for me. So go to the baked status, just pick the loan status because that's the target variable we're interested in. So then once we've picked it, help us to predict logistic regression model on the big data set. So it's combine the predicted output with the predicted output from this and the actual value, which is the loan status from the big data test, and store it in the log pred object here. So it binds to column. It selected this, and whatever prediction is getting from here, it binds them together with this and store it in this. So that's what this particular thing does here. Same thing, this particular one for decision tree, go to the big test, big test data set, select the loan status, then help us to predict the decision tree on the big test. Whatever prediction, combine it, bind it with the one of the loan data sets, the loan variable in our big data sets here. So this is evaluation of this decision tree data sets. Then we have these as well. Now, we've predicted. Now, to be able to see the performance of our models, to be able to see the performance of our data sets, what we are trying to do is we want to predict, we want to take the metric. There's a metric function here in the yardstick package in the tidymodels. So what we are trying to do is like, go to the predictor that we did. The metric function takes argument and estimate. The truth is the actual one is the loan status inside this. If you look at this spread now, let's look at this. If you look at this spread, yeah. Sorry. So you realize that we have the loan status and the predicted class. So the truth here is the loan status, which is the one we selected from the big data set, from the big in the test data set. Then the predicted is this. So when you take the truth, when you pick the truth, use the truth as this, the estimate will be this. Then help us to get the matrix. What this one does is gives you the kappa and the accuracy. So when I do this, I have the kappa and the accuracy here. So it's telling them my kappa, my accuracy is 66%, while my kappa here is just 15%. So I could be interested in having, because at the beginning, remember we talked about confusion, we talk about confusion matrix where we highlighted the sensitivity, specificity, and all of that. So I may be interested in all those metrics as well, not just accuracy and kappa. So in that regard, I will just say, okay, fine. I could use the conf function inside. Let me see this. So if you are interested in other metrics of evaluation, so you can actually do like for instance, these are sensitivity. If I'm interested in how it actually helps us to predict the positive class. So you can look at the sensitivity, the specificity. We are interested in how it actually helps us to predict the negative class. Then we can look at the PPV. We have the MPC. The PPV is the positive prediction rate, which is also the precision as well. Then other metrics are the balance accuracy and all of that. But most times you see yourself not going beyond this first 5 and all of that. So these are other metric of accuracy that you can explore if you're interested in seeing more than kappa and accuracy. Same thing, we do that for our decision tree as well, which is this. I'll go ahead and see for our random forest as well, which is this. Now look at this. If I in my shoe, which of them will you pick? Which of the models do you think you pick anyway? So I'm throwing this question to us. I'm asking a question.
Okay, there is a big challenge. Okay.
Because if you look at it, you look at accuracy and all of that. So let me just let's look at accuracy and kappa anyway. So pick
maybe you, Hamid, maybe you can kind of minimize.
I'm just trying to
minimize the console so that we can see.
Okay.
So maybe that will help.
Sorry. Okay, metrics. I'm sorry. So we have the accuracy for logistic regression is 0.66, that of decision tree is 0.669, and that of random forest is 0.653, and the kappa as well.
I think I will have to break the silence here. Okay, there's some information here.
So
okay, you know what?
Like I said,
sorry,
okay.
Hamid.
Okay.
There's a question here. I think that's why we're having the silence. What is the cap? Maybe okay. So I think they're kind of looking for an explanation now, because we have most people here were new to tidymodels or something. So I'm just assuming that. So maybe you have to break down actually what you want them to select.
When it looks at the before coming in, so we more there's like an accuracy that consider the classes of both of the both classes, but not without any direct interpretation, but it's interpretation of how our model perform. So by class, when you have an data a entire data that is not in balance, like the case we have in our data set, the measure of accuracy that you should consider is kappa. So for instance, say now we have an accuracy of this and we have this, but I rather go with the logistic the logistic regression. Yeah. Why? Because number one, it's closely ties, the accuracy here closely ties with that of decision tree. Yeah. But I think the kappa here is higher than that of the decision tree. So rather, I would rather go with kappa here with this as my method of picking my best model here. So somebody model. So this model is not a bankable model or deployed on mean that 30% of all the times you'll be getting the prediction wrong. That's what 60%, that's what 60-something% accuracy is telling you. That 60% of times you'll be getting the accuracy right, and 30% of the times, 30-something% of the time. So to normally we can't deploy this, but this for tutorial. So you can always work on this using the cross validation, the model tuning, and feature selection and all of that, which is another day anyway, because we can't pack the whole thing. But what I'm saying is the accuracy here, considering the kappa and accuracy, the best model to pick here, the logistic regression model here. So as we can see from the performance of our model, logistic regression model performance based on hence we'll be recommending the logistic regression as let's examine the most important features in our model. So like unlike the random forest package where we've done the variable importance, if it to be that we pick the random forest as our final model, we could just do VIP. There's a VIP package here, which allows you to plot your variable importance for random forest, SG boost and all of that. I think VIP. Yeah. But our selected model is not random forest anyway. Our selected model is decision tree. So random logistic regression. So, and in normal statistics, there's what we call deviance, model deviance for logistic regression. The deviance measures how important our independent variable is. As regards to your data set. So how do you obtain the deviance here? We want the ANOVA here. The essence of it running the ANOVA here is for us to be able to extract the ANOVA table from our fit, our logistic regression fit. Then we order the deviance here. This particular column here corresponds to the deviance column inside this table here, inside this output here. Then here calculated the deviance is in the is in percentage 1 point something, but we based it on 100% so that at least we can have it on a percentage. So that's what we have here. Then we arrange the deviance in descending order so we can have the highest to the lowest and see the first set of variables that are important in our model. So we run this here. And here, when we run this, I'm saying, okay, fine. The head here is that show me the first 6. When you want T shows the last 6. And all that. So the head here shows, okay, fine. If I run this now, I have this. So he's telling me that, okay, fine. Those with the high credit score, having a high credit score, and your recent inquiry being low, your loan amount being high, the purpose of your loan being major purchase, credit utilization being high, and loan purpose being small business. These are major factors actually play critical role as far as the model is concerned here. Then remember, when we are actually trying to read up the case study at the beginning, we were looking for the number of customers to be contacted from say that was given to us. So what we are trying to do with this next slide there is for us to now new data sets. Since we've settled for logistic regression model, then let's apply this logistic regression model on our new data sets to be able to see how many of the customers should they be touched, will be contacted with what our logistic regression says. So remember, this one is just coming up with the data, reading the data sets into our here. So here I'm saying, okay, fine. We are just like the way we did right from the beginning. If we don't remove this variable and we are trying to make prediction with them, it will tell us that they are not of the same size and all of that. The variables there are not the same with the one we use in developing our model. So we have to do the same thing the way we prepare the data we use in developing our model. Same on the new data sets we are bringing in. So yeah, I remove the ID variable, the income joint, and debt to income joint as well. Then I remove the missing values as well. Then remember, we break our data set, the training and test data set. We also need to break these our new data set to be able to make predictions as far as our new data. These are recipes that we pick. Then we bake it on the new data set here. So we want to bake on the new data set here. Now, having done this part here, it's time to apply the model. So what I'm trying to do here is this. So since we settle for the logistic regression model, let me to make prediction of the logistic regression model on the big data set. So when I predict on this big data set, it store the prediction on this. Now, the prediction on this, you definitely have, just like the way we did this here, you have this predicted class here. as your predicted class for your new data set. Now, I'm now saying that as soon as we've run the prediction, then go to the data set that we brought in here, then mutate. Remember, mutate function in the dplyr package help you to add existing help you to create a variable. So you'll be able to add a variable into your existing data set. You can even transform, like if you have, maybe you are given height or weight and you want to calculate BMI, you can use the mutate function too. So the mutate function will help you to do that. So I'm adding a new variable now called loan status, and loan status will be the predicted class that I just predicted from this my new part here, so that I should be able to see the number of people inside these new classes that are in distress and those that are not in distress. So when you play this, so obviously saying that out of the new data set that we have 345 of them that are distress. We can look at the data set. Let's look at this. So what it does is that it's merged. Let's view DT2. So what it does is that it has actually marked this person. So this particular person here is not in distress, but this one is in distress. This one is not in distress. So it's combined them with their corresponding independent variable there. Sorry, then we have, sorry, where is my slide? So I have this. So in concluding, we have in this course, we actually look at machine learning with tidy models. We began looking at some theoretical principles. We constructed 3 learning models using the papers bank, and we realized that logistic regression performed better than the rest. And we identified like 344 customers who are distressed and should be contacted. And what's next here? What should be next is we can look at cost validation. Yeah, cost validation a bit is, let me just talk a bit about cost validation. For us, we can read it up a bit. Cost validation, like I said, is when you have a full data set here. When you have your full data set and you create a training and test here. Test, training, test. Now, you create a cost validation. It can be a k-fold, number of foods you are interested in. So sometimes I do have something less than 10 foods. So you can have like 6 or 7 foods. So 7 food cost validation. What 7 food does is that it will take this your training data sets, divide it into 7 parts, 7 equal parts. So inside this, let's assume we have 3,500 here. As our 500, food 2 up to food 7, all of them inside the training data set. So what we do is like it will create. So when you have 1 to 7 up to 6, 7, so it will start by building the model on the entire on the 4, 6, evaluate it on the 7, on the 7th model, on the 7th. Then inside this training, right, you've not even evaluated within the training there, is trying to do cost validation, validating the data, the model within the training data set itself. And after it does that, it notes down the accuracy on this 7th one, then go ahead and do it has used 1 to 6. The next one, it will use 2 to 7, evaluate on 7, use 5. It will do that for the 7, take the majority, evaluate on the one that has not used, then go to the next one. It will do that 7 times before giving you okay, fine, this is as far as logistic regression, or this is the logistic regression out of the cost validation that I did that is performing very well. So you are not just having a logistic regression, you are having a logistic regression that has gone through series of cost validation to be able to come up with the best of the logistic regression model. So at the end of the day, it does that for the decision tree, does that for the random forest. At the end of the day, you have a model that at least will work better than what we have now, but these are a beginning to the course. Then we have then after you have the model that you have, then you can now evaluate it on the decision tree all of that. Then we have the parameter tuning. Parameter tuning is like when you look at complex machine learning models, they come with more, they come with a whole lot of parameters. They will come with a lot of parameters, meaning that in SG Boost, we have the learning rate, the number of trees to be created, the number of observations to be used at each trees, and all of that. So at that point, you want to be able to do parameter tuning to be able to evaluate how which of the at what levels of the parameter should we pick the final model. Then there's what we call feature selection. Now in a regression problem here, sometimes you may be given a data set. Sorry. Sometimes you may be given a data set with, let's say, 30 predictors and one target variable, having like 31. And a bunch of these 30 predictors may be very useless to your target variable. So, and being useless, number one, they may be very redundant. And at the end of the day, being part of the model building, they may be consuming, because if you are using DigitalOcean, or you are using most of this cloud computing to deploy your model, the fact that you have models that are variable that are just stressing your model will be taking the computational size. Take for instance now, perhaps you are using 100 USD in a month to service your server online where your model is sitting, and there are some variables that are just sitting down there, they are not contributing anything. That means they're just wasting money on computational size. So feature selection is you trying to use your creativity, using your statistical knowledge and domain expertise to be able to come with a feature out of this 30 predicted variable that are relevant, that are very important to your target variable, not just using the entire predictors as a target variable. So one way you do predict feature selection is to start with correlation analysis. Let's assume I'm doing a linear regression problem. If I have something like income as my target variable, and I have salary, I have age, I have weight, and maybe some numeric variable, I can start by doing correlation analysis to see if there is a multicollinearity that exists between these variables. Anyway, take for instance now, two variables may be correlated. If two variables are highly correlated and they are also correlated with the type variable, they may be obstructing each other. Take for instance now, this variable here now is correlated with this, and this one is correlated with it, and two of them are also correlated with each other. I mean, that two of them may be having same contribution to this. I may need to drop one of them, because using two of them at the same time, it's just wasting of time, because two of them are actually contributing to this, and I can just pick one out of them since both of them are correlated. So what have predictors that are highly correlated among each other? You may want to look at multicollinearity. Another way you do multicollinearity is look at VIF, variance inflation factor. So like scholars agree that when your VIS is more than 10, then you drop that variable that has a VIF more than 10. Some argue that if you have like 4, this is analytics anyway. There are a lot of journals, so many discussion around this. But the most important thing is that when you do your data visualization and you do your scatter plot and you see that some variables are correlated, you can remove them. That's another way of doing correlation. But for a non-linear regression problem, aside from doing correlation, I can do chi-square. Chi-square as well, looking like, okay, fine, I have a TJ variable that is take. For instance, in our case study, we have loan status, and we have other variables like credit score, which is either ion or loan amount or something, or maybe employment history, which is recent or something. I could do chi-square. Chi-square is just you trying to see the relationship that exists between contingency test anyway, to see the relationship that exists between two categorical variables. So if there is any relationship, they are dependent. If anything exists between them, then fine, use that part of your predictors to go ahead. But if they are not related, if there's no anything related within your target variable and one of the predictors, which is categorical variables, you want to drop it, and so they find since this one does not have any relationship with my target variable. So there are so many ways you do feature selections to be able to come up with features that you think that can go ahead of that. But it's something that comes with subjectiveness and coming with also domain expertise. because I believe that if a model that goes through feature engineering and selection will definitely perform better than models that didn't pass through all these steps and all of that. Any question around there?
Do we have questions? I think a lot of terminologies has been used so far. Please, if you have questions, please just signify. Sorry, are we still together?
Yes, we are still together.
Okay. Okay. I think we're using the time well. So I think maybe you should go ahead and just let's conclude, then we'll give time for comments and questions.
Okay. So moving forward, I think we're almost at the end of the slide. So this is a reference. This is a book I usually recommend for anyone who is trying to get started with machine learning, and because definitely no matter how black box a model is, it's always good to start with the most simplest model, because at least you want to be able to interpret what's going on in your model. If you realize that at the end of the day, when you fit your simple model and the accuracy of your complex model perform better than you stick with it. But sometimes it's not, you don't start with just start, okay, I want to start the machine learning algorithm now. The list, and I'm doing a classification problem. No matter how simple the model is logistic regression, I always start from logistic regression. Then I can now move down to random forest, SG boost, other boost, and all of that. So what this book actually does is basically introduce you to some statistical concepts like p-value, adjusted R square, mean square, like in regression time. Also, there are also models in regression apart from linear model. You can do ridge regression, lasso, where you introduce some penalties into your model to be able to, because most problems there are not always classification, it can be linear, but how do we make sure that our linear model is also performing very well? Also polynomial. So you can actually look at this book. If you need it anyway, I think I can send it to the convener. I can share it with you guys. But at least it's a book you can get started with and learn most concepts in machine learning model. So I think that's the question. That's it for today. Any question, please?
Okay, please, we'll really appreciate you sharing the book with us. Then we can send it to Meetup as well as our WhatsApp group. Thank you so much. Okay, so if we have any question, please, our instructor would like to take his leave by 12 noon because he's having another class that is clashing with this webinar. So please, if you have any question before we allow him to go by 12, so he would really be glad to answer those questions now, so that we can continue sharing resources with each other. Questions, comments?
So somebody is asking that what's the difference between sensitivity and precision? So it's something that I usually confuse. In fact, I can tell you that a whole lot of data scientists are always getting those metrics confusing. That's why you use confusion matrix. That's why they call it confusion matrix. So basically, what the idea I usually use for sensitivity and precision is this. Like I said the other time, always start with a confusion matrix. So let's assume we have a confusion matrix, which is this is predicted here, predicted classes. Our classes can be either positive or negative. So which your positive can be the defaulted on loan and your negative can be not default on loan, whichever classes are used. And we have the actual here, which is either positive or negative here. Now, assuming you've come up with your two positive, two negative, and all of that. So let's assume, I believe by now maybe you understand how to come up with this by the example I did the other time. So let's assume these are two positive here. These are false negative here. These are false positive. These are two negative here. Now, like I said, accuracy is you taking all these guys here, divided by the two positive four. Accuracy is you taking these diagonals here, then divided by all these other ones, two positive over. So that's accuracy. But sensitivity here focuses more on this part here. So the predicted class that were actually positive class that were correctly labeled. So what we are trying to say is that in sensitivity now, what you'll be doing is just have two positive here all over these two positive plus false negative. So this particular here is sensitivity here.
Hello?
So actual observations, they will be positive inside your actual now. These are as well. So sensitivity is also something, the same thing. But there's what we call process on this. As those were the two positive, they were correctly predicted as two positive from your predicted classes. So this one is from the actual classes. This one is from your predicted classes. So the two positive that were correctly predicted as positive from your, in your prediction, is it that you have two positive, the one that were truly classified as predicted, and the one that were falsely classified, which is positive, and the one that were only classified as positive. So in precision now, what you'll be having in precision will be this equals two positive or two positive plus false positive. So that has a major difference between recall and precision. So why you use with precision? Oftentimes, if my intention, like take for instance, in medical sciences now, I don't know, I can throw this question. Some people argue that being classified as having cancer, for instance, somebody who has cancer and those who don't have cancer, being classified as having cancer when you don't have cancer could be better than having cancer and being classified as not having cancer. Because at least if you don't have cancer and you're classified as having cancer, if you go to another part, it may be seen that you don't have cancer. Although in some cases, some people might commit suicide, which is something else. But what we are trying to do is that in some cases, you might be considered about those that we actually have cancer, that were predicted as having cancer. Are you getting the point I'm making? The proportion of people that have cancer, they were actually predicted as having cancer. Not the proportion of people that have cancer that were predicted as not having cancer. Do you get the point I'm making? So if a particular class of your type variable is what you're interested in, the positive class of your type variable is what you're interested in, not the entire accuracy of those, the one that actually predicted both classes correctly. You may be interested in the one that actually predicted a particular class of your type variable correctly. Then you may thinking of precision as your measure of accuracy. Do you get the point I'm making? Sometimes you may be interested on the one that actually, we may be interested on the one that actually help us to predict, maybe in loan status, loan cases now, we may be interested on those that defaulted, not those that did not default. We want to be able to build a model that actually predicted those that defaulted. So in that case now, and default is maybe our positive class, then we'll be thinking of using precision as a measure of accuracy. I don't know if I answered that question.
Okay, there's a follow-up question. Does it mean that the reverse is the specificity? Does it mean that that's the
Yeah. Specificity, yeah. There's also specificity as well, which is also you are focusing on this other part here. In specificity, you are focusing on this part. You are looking at the two negative all over, two negative all over false positive. That's specificity. So those metrics they can be confusing, I understand, but at least when you sit down and look at it very well, you realize that just requires logic for you to be able to differentiate between them. Any other question here, please? Are we here?
Okay. Do we have any other question? Okay, we're getting a big thank you from the chat box. So thank you so much, Hamid. We've really enjoyed a wonderful time with you despite your tight schedule. And we really appreciate that so much. So like we discussed, we will look at some case study as time goes on. So depending
Can you hear me
on,
now?
yeah, we can hear you now. Can you hear me?
Hello?
Hello, seems your network.
I can't hear. Is it my network?
Your network. Hello, can you hear me? Hello, Hamid?
I can hear you, man. But Mr. is not coming up.
Yeah, I can hear you. Can you hear me now, please?
Okay, yes, we can hear you now, loud and clear. Okay, thank you so much for the response there. Okay, we want to use this opportunity to thank you so much for honoring our invitation. And like we discussed, we will look at some more case studies depending on your availability. So we really appreciate everybody that has joined us for the webinar today. And we want to, on behalf of everybody, say thank you so much, Hamid, for a great presentation. We love the walkthrough, the slides. We're really grateful, and from the chat, everybody is appreciative of that. Thank you so much. We appreciate that. So we'll look forward to you sharing the book that you mentioned so that we can share with all the participants via Meetup. So I'll follow up with that with Hamid. And on this note, I want to say a big thank you to you once more. I will really appreciate that. Then to everybody, thank you so much. So on behalf of Abuja, our user group, and our ladies Abuja, was saying thank you and God bless you all. So we look forward to seeing you some other time. So we're going to share.
Okay, thank you, everyone.
The video is going to be available on our YouTube channels. So we're going to do that before Monday. You should have it. And we'll also share on the WhatsApp group and on all our social media pipes or whatever. So we'll do that. Thank you so much. And we really appreciate you. Thank you. Thank you.
Thank you, everyone. Bye-bye.
Bye, dear. Bye-bye. Bye-bye. Thank you so much. Thank you. Bye-bye.